with Yu Xingge and Jie Qing, and also some recent work with Paul Yang and Rubin Zhang. Okay. So mention some result. So first, I'm getting confused. Okay. So the problem we are studying is the following. Given a compact manifold, my manifold is MD minus 1. So sometimes I denote this D minus 1 by N. So this n-dimensional manifold. When it is the boundary of another manifold, and that is XD, and with a Poincare metric, Poincare-Einstein metric. And the relation between this H and the Poincare metric is you can have a defining function rho such that rho square G plus. The G plus is a non-compact manifold. You multiply it by rho square so that it's a compact metric and whose restriction on the boundary is the given H. So you ask your question, when does this happen? And of course, the model case to keep in mind is the sphere is the boundary of the Poincare ball. Okay. So this is the problem of conformal filling in. And as far as I can tell, it's first raised by in an article by Marticina in around 1998, but it's also mentioned in articles by Wheaton. And of course, geometrically, this what we call conformal compact manifold is a subclass of asymptotic hyperbolic manifold. Asymptotic hyperbolic means the sectional curvature tends to -1 on the boundary. So this happened to be true. So asymptotic hyperbolic metric is well studied. This is a topic of study in geometry. So first, I will give a brief survey about the progress made on the problem, and then I will concentrate on the compactness problem. And then I state some perturbation result and some uniqueness result. And then I will state some compactness results for not a perturbation case, a general case. And then I have already in the first 2 lectures laid a lot of background about the proof. So here I will outline the proof and use these backgrounds. Okay, so let me repeat what is this CCE manifold, which is already mentioned repeatedly in the last 2 lectures. So there is this defining function rho, and then this rho is not uniquely determined. So that means you have a rho, and then you have another metric in the same conformal class of rho, and we denote that by this bracket of rho, conformal class. And then in that case, we say the boundary, the conformal infinity. It's not a boundary, it's conformal infinity. And we wonder if there exists such a C. G plus is the Poincare-Einstein metric. I normalize so that its receipt is minus NG. And one thing I repeatedly use is, given a CCE manifold, there is a special geodesic defining function, special defining function, we call it a geodesic defining function, and which on the boundary is the distance is really look like the boundary distance metric in an asymptotic neighborhood of the manifold. So I refer to it. So this is an existence result. And now let me record a typical example we are looking at. The first example is the hyperbolic space, upper half space, RD plus. And unfortunately, I use a different notation in range. My X is the RD, and my y is this vertical direction.
It's the wrong choice.
Okay. I'm sorry. X is the y is the vertical direction. Anyway, I thought I used do we have the same convention? I forgot. Okay, anyway. And this is not really CCE in the sense that even you multiply this hyperbolic metric by y squared, you get a flat metric, but it's not compact. Okay? It's no longer compact. So it's not CCE, conformal compact, but it's conformal Einstein. But this is a model case, as we will see that we frequently study the blow-up limit of a sequence of CCE manifold, and that's the limiting space we are targeting. Okay, so this is the model example. And then the second example to keep in mind is the sphere with hyperbolic ball. And so we have this Bn plus 1 and Sn, and then there's this Poincare-Einstein metric. And this metric is really, I write this as equal to 1 minus, you can write it as 1 minus x squared. I try to save x for other purpose in the lecture, so here I denote it by 2y squared. So y is a point on x Bn plus 1. And this metric, for this metric, it turns out the geodesic defining function is not that obvious. It's rho equal to 2, 1 minus y, or 1 plus y. Usually, the geodesic defining function is only defined in an asymptotic neighborhood of the conformal infinity, the distance. But for this one, it exists on the whole ball, except at the point y equal to 0. So this is, that means this gradient rho is equal to 1 throughout the ball. So the geodesic function defined everywhere. And then with respect to this geodesic defining function, this rho squared g plus is not canceling out this factor completely, and it's actually equal to d rho squared and plus some number 1 minus rho squared over 4, and then gs. Okay. So restrict to rho equal to 0, it is GSM. And the other thing which turns out to play an important part in this approach is, no, if we are really on the ball center at 0, this rho is equal to exponential minus 2r. That's why I use the notation rho. Well, this r is the distance in hyperbolic metric from the point y to 0. Okay, so there is a relation. Log rho over 2 is the hyperbolic distance. Something to keep in mind. And now, of course, there are a lot more other examples, specific examples. And another important example to work on this field is somehow that given a boundary and the same boundary, there may be different extension, different filling in of the manifold. So an example is the following. If the boundary is S1 lambda, the lambda means a circle of radius of length lambda. S lambda cross S2 with the product metric. Then, for certain value of lambda, there may be 3 different types of filling in. Let me describe that. It turns out that one type of filling in is you have the circle S1 cross S2, you fill in S2 with the hyperbolic space. S2 become B3. And somehow S1 lambda stay. So the extension, the topology is S1 lambda plus B3. And there you equip it with a hyperbolic metric. And this extension exists for all lambda. Okay. So one can write down this. But it turns out that for other lambda, if for lambda x, there is other way of filling in. And that is you keep S2 filling in with D2, and S1 lambda becomes the ball. Okay, so it can become B2 cross S2. You fill in the S1 part, that part win over. And then in that case, you have this famous ADS Schwarzschild space, which I write down. We don't need to know much about it, but one thing I pointed out is it turns out for lambda less than this special number, 1 over square root of 3, given the same boundary, there are 2 ADS Schwarzschild filling in with different mass. Okay, M is the mass. Okay, so there is a non-unique filling in example, and that's a parking page example. This example is well studied in math and physics. Okay, and given that, let me say a bit about the general existence result. So there are special examples for special cases. But for general existence result, actually we know very little. And the fundamental paper is the paper by Pfefferman and Graham in '85. They call the M-beam metric construction. Their construction is given MD minus 1, they actually add 2 dimensions and it becomes a Minkowski space. But a slice of it is what I'm describing. Given M, you can fill in with a Poincare Einstein metric in a neighborhood of M. Okay, and original work by Pfefferman and Graham is to deal with H, which is real analytic, and later on, the work of Zworski and Zworski did it for smooth H. Okay, so this is ambient metric construction. And then the other existence result is the perturbation result of Robin Graham and Jack Lee, which they show that if you have the standard sphere, you perturb the standard sphere H in a C2 alpha neighborhood, and if that neighborhood is sufficiently small, you have a filling in. And for the standard sphere, the filling in is hyperbolic metric, and the metric which Robin, Graham, and Lee constructed is also in a neighborhood of that hyperbolic metric. So it's a perturbation using this implicit function theorem. This result is a special case of a later result of Jack Lee. And Jack Lee saying that under other conditions, if you have sectional curvature of the interior of a metric is negative or close to -1, then you have a perturbation result. Okay, so but the result I want to quote is Graham and Lee here. And then there is a non-existence result by Matt, Han Qing, and 2 papers. The other one is Zworski, Han, Strauss. I will not state the full statement of the result. They have a large class of manifold where you don't have extension. And in particular, a special case of the result is S4K minus 1. And when K is bigger than equal to 1, well, bigger than equal to 2. So for S7, they have a class of metric on S7, which is of positive scalar curvature and they show that this class of metric do not allow CCE fill-in on B8, okay, for example, S7, and they use index and so on. But the one crucial thing which they did of the reason why this such example exists is based on the result I already mentioned of Jack Lee and Jie Qing. That says if your filling in exists for metric on the boundary, which is positive scalar curvature, then the interior has to be positive scalar curvature. That's where the contradiction of Zworski, Han, and so on comes in. So, okay. And if one look at the result of Zworski and Han and so on, one notice they need S4K minus 1, and for k is bigger than or equal to 2. So question is what happened on S3? Okay. So on S3, so one special question is, what are the class of metric on S3 which allow filling in? And especially if you have this H is a positive scalar curvature. And this class is different than, say, S7 in two ways. And the first is because the class of positive scalar curvature metric on 3 manifold is path connected. Okay, and that's a result of Fernando Marcos. And then you see that for this class, the index argument for non-existence of Zworski and so on does not apply. I didn't go into detail about the proof, but the proof is this. Okay, so that's the question I have been working on for a long time. We are getting close, but we didn't answer the question yet. Okay, so and in today's talk, I will mention the compactness problem. So that means given an H, we know that the interior may not be unique. But on the other hand, we can ask if you have a family of metric HI on the boundary, which are compact, and if you have extension inside, that extension inside is also compact. So we want a parallel bound, okay, a parallel bound of the interior metric controlled by the boundary metric. We are studying the boundary value problem. And this problem is formulated modular conformal class because in the conformal infinity, only the conformal class of H is fixed. And when you talk about compactification, there is also this conformal factor. So this is modular conformal factor. So we want GI restrict to the boundary is HI. And what is the difficulty of the problem? The difficulty of the problem is because there exists a local term. If G is an extension of H in this sense, then we know there are expansion of G. The term is not depending on information of H only. So, and this is expressed in the following way. Say I'm talking about special case 3 dimension, then we know that this G has this asymptotic expansion, D rho square plus H, and plus a G rho term is 0, and then G2 term is a G, the rho square term G2 and G3 and so on, power series expansion. And one knows that this second order term G2 is just the shortened tensor of H. It's a combination of H and so on, depends on H. But the G3 term in this computation is DD normal of the resi of the metric. So wherever you have a DD normal, and that becomes the local. The local for me means that the behavior of this function at one point does not only depending on its behavior in a neighborhood, it depends on what happens at other places on the entire compactification. So it's like the Dirichlet-Neumann problem. So this, if one think about the receipt of G as something like Laplace G, the second derivative of G, then this is a higher order Dirichlet-Neumann problem. So in three conditions, the problem we are formulating is, suppose this G, we know H, and then under what condition do we know G3? If we already know this is a CCE manifold that exists in G plus inside, does that mean G3 is already conformal? Under what condition it is conformal? Okay, and before I say that, H together with G3 determine everything. Once we know H, once we know G3, then we know the entire expansion of G. So this is the only missing information which we try to capture. Okay, and now I want to set up the problem. Set of the problem is, because this problem is modular, everything is modular conformal class, then one wants to say what is a good representative, so the problem is better controlled, okay, better controlled. So for that, we have these invariant things which are independent of the conformal class. For example, N manifold is the Yamabe constant, and on compact manifold with boundary, we have two types of type 1 and type 2 Yamabe constant, which I discussed in the lecture 2. And then there is another conformal invariant, conformal invariant quantity, which is the Weyl curvature. So Weyl measure somehow if the metric is locally up to conformal class, the same as Euclidean metric. So there's the Weyl curvature. It turns out this Weyl curvature is a pointwise conformal invariant. That means a Weyl up to a change of coordinate G to G theta is just pull out a conformal coordinate pointwise thing. As a result of this, this is a pointwise conformal invariant in this sense. And then on a dimensional D manifold, the Weyl D over 2 dVg is an invariant quantity. That is, if we use G or G theta to compute it, this term is the same. So in particular, when I'm dealing with full manifold, I know Weyl L2 norm is a conformal invariance. So those are the invariants we try to see if we can control. Okay, so to set up the problem on the boundary, it seems it's convenient to choose the representative to be the Yamabe metric. Okay, so constant scalar curvature, so it is easy to handle. And now, how about in the interior? How about in the interior? In the interior, for the compact manifold with boundary, we also have Escobar's result tell you you have a constant scalar curvature metric, the Yamabe metric. But why can we just try to choose if HY is compact and the GY is compact? The problem is we do not know in the interior we solve the Yamabe problem. We do not know that Yamabe problem GY restrict to the boundary. What is its behavior? Okay, so there is another conformal factor. We do not call to control GY restrict to the boundary to the HY in some sense. So instead, what the approach we are taking is, given HY, we try to choose a representative whose boundary is already this HY and deal with this compactification. Okay, and this is the class of metric which I have discussed in the first two lectures called adapted metric. Adapted metric is this metric whose boundary, I should say G in the no plus, or compactification G, whose boundary restrict to the boundary is the given H. Given H, you solve some PDE whose boundary is this. Okay, so that's the thing we try to do. Okay, and given this explanation, let me say there are a couple results. The first result is, for simplicity, I frequently deal with the conformal infinity is just the sphere. Okay. And in some cases, you don't need that, but let's assume it's the sphere. And then our basic assumption is always, we assume on the boundary, everything is fine. So we assume on the boundary, we have a class of metric, which is in suitable CK alpha topology, compact family. And we assume this HI, for example, has stellar curvature bounded from below, or it's Yamabe constant bounded from below. I always assume that. And then the perturbation result says that then suppose, say, let's look at condition 2 double point. 2 double point says if the boundary Yamabe constant is sufficient, we know this Yamabe constant is always less than the Yamabe constant of the standard sphere. But suppose it's sufficiently close, then this class of adapted metric after diffeomorphism is compact. Okay. So, and then I have left it ambiguous what's adapted metric because there's a family of them. Which one do you choose? And I will be more specific later. It turns out the choice is, I will remark on that. So there is this result. But another point of this result is, it turns out we can either assume the Yamabe constant is sufficiently close to the sphere, or we can assume the interior metric is GI plus the YL2 norm is the same as its closure because it's a conformal invariant. So we can assume that's sufficiently small. Okay. Either condition leads to compactness, but we only need one of them. And then after the compactness, we will show uniqueness in this class, so that indicates these two conditions are equivalent. Okay, so if you have a boundary metric which is close to the boundary Yamabe constant, it turns out the GI plus you choose to filling in after existence result of that metric also have value L2 norm small and vice versa. These two conditions are equivalent. Okay, so we only need to assume one of them, but after that we see they are the same. They are the same. So that's the first perturbation compactness result, which I will explain more later. The second existence, okay, that's a perturbation compactness result. And there is some application of this perturbation compactness result, let me say that. And there's a uniqueness result. Uniqueness result says the first uniqueness result is by CHANG in 2003, but then later there is a proof by Dutta and Jebahari. They show that if your boundary is the sphere, then hyperbolic ball is the unique filling in. Okay, unique filling in. And the original proof of CHANG actually used a positive mass, but the later proof is more geometric and doesn't rely on positive mass. And a consequence of this perturbation result is uniqueness theorem 2. Uniqueness theorem 2 says if you have perturbation result for a metric H in a neighborhood of the canonical metric, Jack Lee and Robin Grant's extension is also unique. It's also unique. And the reason why that is true is the metric they constructed is in a perturbation neighborhood of the hyperbolic ball. But our compactness theorem says the limit is also hyperbolic metric. So any other metric you have the extension is already in a neighborhood of hyperbolic ball. So as a result of that, you need an argument to put it in the right weighted Sobolev space. And then that says in that small neighborhood of hyperbolic metric, the existence is unique. Okay, so the uniqueness is a consequence of the compactness theorem. And as a result of this uniqueness, we know those condition 2 and 2 point are equivalent. Okay, so, and it turns out there is also an application of this uniqueness theorem in the case of this S1 lambda plus S2. So in that case, we know that S1 lambda plus S2 have, with the product metric, have different filling in. But this theorem says that only can happen when lambda is small. It says that if lambda is sufficiently large, then this S1 lambda plus B3 is the unique filling in. Okay, that's for lambda sufficiently large. And the reason why that is true is it turns out in this case, S1 lambda plus S2 and with the product metric, if one computes its Yamabe constant, and the result of Rick-Shen says when lambda is very large, this Yamabe constant tends to Yamabe constant of YS3. And if the limit constant is the Yamabe constant is the standard thing, then our compactness theorem applies. So in this case, we also have uniqueness. Note that this result only holds when lambda is big. When lambda is small, we do know there exists other extension. Okay, and what is the critical value where you have different extension exists is an open question. We do not know if this 1 over square root of 3 is the critical value where the bifurcation happens. You have different extension. Okay. So, okay. And this result also somehow echoes the work of Zworski and Han, and we also have non-existent result. And that non-existent result happened to happen for all dimensions. It says that if your Yamabe constant is sufficiently close to the standard case, then the only topology which allow an extension is the ball. Okay, so if you have this B, this domain, and if you say even for a ball, you chop off something, this is your manifold, you can still keep its boundary to be, say, this is SD minus 1 there. You can still keep its boundary to be close to the boundary on the asymptotic ball. But the non-existent theorem says, suppose this is not topologically the ball, there is no extension. No extension. Because the compactness theorem tells you the limiting case has to be the ball. Okay. So one has extension theorem. So, and that's a perturbation compactness. So now let me say some general compactness theorem in 4 dimensions. And there's other version for D dimension, but let me concentrate on 4 dimensions. The 4 dimension says the general theorem we have is the following. So we assume this boundary compactness, boundary metric 1, we always assume. And then it turns out, in this case, we need to add an assumption. And that assumption is the while L2 known is bounded. L2 known is bounded. And then, given control of these two conformal class, we want to say the sequence of GI is compact in CK alpha. And in a proof, there are also the complication. You want to deal with the blow up, either happen in the interior or happen on the boundary. It turns out to prevent the interior blow up not to happen, you need to put constraint on the topology. And that's this topology you put it on H1 and H2. XZ is homology is 0, and that prevents the interior blowout. And the first two conditions would prevent the boundary blowout. Okay, so that's our compactness result. But in this case, I have to say the adapted metric we choose is the scalar flat one. So I will explain that. In earlier work for other compactness result perturbation, we have freedom to choose a lot of adapted metric. In early work, we choose the Plattman-Graham metric. But later on, we are forced to deal with this metric. And I will explain the reason why. Okay. So recall what's this adapted metric. Okay, adapted metric. So let me follow the transparency and explain why I choose the scalar flat adapted metric now. Okay. So in the proof, there are 3 ingredients. In the lecture, the first 2 lectures, I tried to give a lot of background on the first 2 ingredients. The first one is control of the Yamabe constant, which I talked about yesterday, that if the boundary Yamabe class is greater than or equal to 0, then we want the interior Yamabe metric to be greater than or equal to 0, greater than 0. Okay. We want to control the boundary interior Yamabe invariant by the boundary Yamabe invariant. And if the boundary is bounded away from 0, then the interior is bounded away from 0. That's what I talk at the end of my second lecture. That's the first ingredient. And then the second ingredient I also spend a lot of time talk about is what we call adapted metric. Adapted metric, recall, is defined by the following way. We have this CCE class. We look at the Poisson equation. This D minus 1 is my N. So there is a minus Laplace minus Sn minus V equal to 0. And then if we choose, in this CCE setting, if we choose the Poisson, the Dirichlet data F to be 1, then this V is positive. This solution is positive. And then we choose a special metric. We use that V to the 2 over n minus S power as our conformal factor. We call that adapted metric. Okay. And so that adapted metric is with this special setting with a solution. And this G restrict to the boundary is the given F, H. So let me say this row is chosen depending on H. So this row equal to 0 correspond to the fact this G star restrict to the boundary is my H. Okay. So we have a lot. But then the problem is there are a lot of such adapted metric. We can run the index S, and when S equal to n plus 1, that's my example 1. That's the Jackley metric. which has the property, if the boundary Yamabe constant is positive, then the interior scalar curvature of the matrix is positive. And it turns out this GS matrix has a family, and let me try to say that why do we choose this special adaptive matrix? So we have a family of matrix GSR. This S say is in 1/2 to infinity and subtract n. And the index in some modification to Platinum Grand matrix. And then it turns out that for S in the range of 1/2 plus 1L to infinity to say n plus 1, and say subtract n, actually including n, if one understand that as the Yamabe Platinum Grand matrix, then this matrix is totally geodesic. If the boundary scalar curvature is positive, that will imply the interior is positive. And the fact it is totally geodesic is to our advantage. And the reason for that is, if one look at the Gauss recall, for Gauss-Bonnet formula, if we have an X and with a boundary G, and the Gauss-Bonnet formula has this wire square on the interior, and then there are two terms, and the two terms is 6 times R square minus 1/R² minus 3 of traces VC squared. Or, I'm sorry, the other way to think about this is R² minus VC squared. And if G is without boundary, so there is a complicated boundary term. But if G is totally geodesic, then BG is 0. So that means we don't need to handle boundary behavior. So it looks like if we are going to deal with any metric, we should choose such one, because in this range, because it's totally geodesic, we don't need to handle boundary term. But the difficulty for us is, in this formula, we do not see how to show the scalar curvature of VC squared is finite. So the difficulty is why the integration of RG VCG squared is finite. We are not able to show this for any of the adapted metric, projective metric. You know that this is positive, scalar is positive, and but there is this negative term. Even you assume Y is bounded, your VC is bounded by scalar square. But the scalar square, we do not see why the scalar square is finite. We do not see that. Okay, we try very hard to say why this is finite, and we do not see it. And for that reason, we are forced to deal with the adapted metric, which I discussed also in my first lecture, for S equal to n/2 plus 1L, and that we call that the adapted metric. And that has the property that the scalar curvature is flat. For this particular index, is flat. And if it's flat, then at least here, this term is 0. Okay, so that means the RISI L2 norm is bounded by the boundary term, by the while L2 norm, another conformal invariant. But then we need to handle boundary term, because now we have this G is unlimited, but not the mean curvature of this metric G star with the boundary given is positive, okay? But it's not 0. So we need to add a boundary term. So we pay a price, and that price is we need to handle boundary term. And the advantage is we have L2 norm control. We see bounded by bio L2 norm plus the boundary term. So it depends on how boundary is, we have a better control of the situation. And it turns out that this is the thing I explained in my class in the lecture, that the reason for that is if one examines the boundary term, the important thing for this formula here is the negative sign there. So I need to. Okay, so this time. Okay. So the important thing here is here the scalar is equal to 0, so that turns wrong. So we have a negative sign here. But if I examine carefully the boundary BG term, in this case, is scalar curvature of H times the mean curvature and minus the mean curvature Q. Okay, it's precise constant, not important, but the sign is important. So what does that say? That says that if you have the vial L2 norm control, and if you know the scalar H, the given information, you know the RISI in L2 and the mean curvature L3 norm is bounded. That's a key fact we will use. So for this metric, we have adding the assumption the vial L2 norm is bound, we have curvature in L2. And that's the important property we will use. Okay, so the key property is the scalar is 0, the mean curvature is positive, and then the third property is one also have the distance is a defining function working like distance function. The gradient G star rho is less than equal to 1. And the fourth property is we now have curvature L2 norm. And then the fifth property is this is common for all G star, and that is it is conformal to Einstein and hence Bach flat. Okay, so this other property I didn't explain in class is conformal to Einstein, and then it is Bach flat. Bach metric is the critical metric of L2 norm of vial L2 norm. And it turns out this condition is a conformal invariant condition because vial L2 norm is conformally invariant, so its critical metric is conformally invariant. Einstein is in the critical metric, so its metric conformal to Einstein. So conformal metric satisfy PDE, which is Bach flat. I did not go into detail here. And in this case, it happened to be an elliptic system. And so one can use that to gain the regularity of the metric. So elliptic system help you to gain. If the data is C alpha, then the metric is in C2 alpha. And later on, what we will use, we want to gain a little bit. We're saying that if the metric has the curvature equal to 1 at a point, then in a neighborhood of that is close to 1 in a better topology. Okay. So property 5 eventually leads to greasy decay property for the rescale metric, which I'm going to explain now. Okay, and now there is a third ingredient in the proof I didn't mention in my first 2 lectures, and which I'm trying to describe now. So this third ingredient is this what we call LQS inequality. This is LQS inequality is derived by looking carefully the proof of Dutta-Jevahiri's proof of the uniqueness of hyperbolic metric, and then reformulate the statement. And the other thing they do is, it turns out in the Dutta-Jevahiri proof, they didn't handle the cut locus point of the manifold. So there's more detail to fill in. So here is the inequality. This result holds for any dimension, but let me state it for dimension 3 plus 1. So for d equal to 4 case. And this inequality also holds for a class of asymptotic hyperbolic metric, but in particular it holds for CCE. So let me state it for CCE. So first, there is this volume comparison theorem, which says if you have a metric whose reason is greater than or equal to n, then you can compute the volume of a ball of radius t to the volume of the hyperbolic ball of same radius, which turns out to be a monotonically decreasing function to t, and is less than or equal to 1, but it's also greater than or equal to volume of G plus in the boundary of Bt. And then, so that's area, and VGH of boundary of Bt. This is a classical global Bishop comparison theorem. So on hyperbolic ball. But what the LQS inequality is to say is, on the CCE setting, you can compare this ratio of the area at a lower bound. And that lower bound is the Yamabe constant of the manifold on H divided by Yamabe constant of S on the canonical metric into a suitable power. D minus 1 over D or something like that. Yeah, so there is a, it means T equal to 4 is 3 over 2 power. So that's the inequality. So it's this. And an immediate consequence of this theorem is the result, the way of Dutta is Jevahiri. And what they say is, this shows if the Yamabe constant is the same as S3, then G plus is isometric to GH on both. Okay? Because then this is 1, and we know this is less than or equal to 1, and attend 1 is only when it's another case. So this is their proof of this uniqueness. And how does one prove this thing? The proof is quite empty, especially if one wants to handle the cut locus. But later on, we'll actually use the strategy of the proof to get our compactness result. So let me describe the strategy of the proof, the key point of the proof. The key point of the proof is the following observation. So we have this metric G plus, which is rho square G plus. This rho is the geodesic defining function. But we also have this metric G plus, which is this Ricci G plus is minus Ng plus. So you can consider another compactification, which is using the distance function of G plus to compactify it. So you define a variable, a t of x, which is defined to be distance in G plus of x to a model point. So you have fixed a point, you consider T4. And this T4 is the distance in G plus metric. And then this metric, we have, say, G theta is equal to e to the minus 2t of G plus. Think about this compactification. So we have two compactification. One is using geodesic defining function, and the other is using distance function. And the idea is these two things are in the same conformal class. So we try to estimate the information we want about the hyperbolic floor using this compactification. So that means the picture is the following. So you have this fixed point, and then you have gamma t, which is boundary. Now you are interested in compute the area of gamma t using this G theta t metric. Restrict to t called G theta t. G theta t is G theta restrict to this 2t4. Gamma t. So this is a GT metric. We are interested to compute the volume of this guy. And then the idea is, so here is my conformal infinity. I try to use this sigma r and then G theta r to compute. So what is this r? It turns out, looking at the model case, this r should be defined by the rho. The geodesic defining function is take log of that 1/2 negative that should be by r. Because in that case, in the model case, r is the same as t. Okay, so the point is, we now write this G theta t as equal to t to the minus 2 t minus r, and then gr of this g plus. And that is my g bar. So this is equal to, I define this. So if I think about u equal to t minus r, consider this function. This t of r, using a little bit of computation, that actually just triangle inequality. It turns out this u is bounded. Okay, so you have this. You think about this as equal to psi to the 4th power g r theta, where psi is equal to e to the 1/2 of t minus r. So instead of computing it using GT metric, we try to compare GT to GR theta and compute the area of this level set gamma r. And why does the Yamaji constant comes in when you compute? So instead of computing this boundary using that metric, we use a conformal class to compute it. And why does that number comes in? And that's because if you think about this thing on gamma r or on gamma t. This side, right this way, has relate the scalar curvature of GT theta to GR theta, GT bar to GR theta. GT bar to GR theta. So, and the relation is 1 is R of G theta, and psi to the fifth power is minus the plus G psi plus 1 is of R of G bar of psi. That's just the prescribing curvature equation, and then you are trying to say that I know the behavior of R G bar because it's this function is a hyperbolic distance, and I have this RG theta. I'm sorry, the notation is a little bit. I know this RG bar because it's the geodesic defining function in asymptotic neighborhood. RG theta is the term which is to control this constant. Okay, please treat to that side. And there is a complication. So the key thing is to look at this PDE and then trying to see integration of psi to the sixth power is computing the area of this sigma r, and then you have this control of the constant, which is the Yamabe constant. That's the basic thing. So use the conformal invariant property of this matrix. So that's this LQS inequality. So, and now let me say that given that it turns out our perturbation result is a direct consequence of this JR LQS inequality. So one can view it that way. Sorry. Okay, so I will come back to the perturbation result. So recall this is the result I'm trying to show. Okay, I'm trying to show. Now let me outline the proof of the main theorem and the perturbation theorem. Okay, and as I said, the main scheme is trying to prove things by contradiction. Okay. So the step one is to say the Yamabe constant in the interior shows that this GI bar closure of that have a uniform injectivity radius. Okay. Sorry. So proof by contradiction means suppose given this sequence GI, which is my GI star bar, does not have the behavior we want. For example, if its curvature is not bounded, it begins to blow up. Then we rescale it to make it bounded. Okay? So that's what I call GI bar. And then the first thing is to notice in this rescaling, we have uniform injectivity radius for this once its curvature is bounded. Okay? And that somehow use the Yamabe constant control. Yamabe constant is invariant under scaling. And then the second step is to show this sequence all satisfy this Bach equation. So there is epsilon regularity, and you get some regularity. And then the important step is to say no, there's no boundary blow. I will talk more about how to show that later. And then the next step is show there is no interior blow up, and that's use these topological assumptions. So now I will begin to say why there is no boundary blow up. Okay, boundary blow up means the blow up points. There is a distance to the boundary, to the blow-up point which approaches boundary. At least it doesn't approaches to infinity, conformal infinity. Okay. Okay, so that's an outline. So, and now I will spend some time trying to prove step 3. Okay. First, I prove step 3 in the case of perturbation result, and which turns out to be a direct consequence of this LQ SE party. So perturbation means I'm already perturbed in a neighborhood of the standard metric on the boundary. Okay, so the first thing is that if this GI has a boundary HI is compact, that's our assumption. Then if you take his scale metric, then its scaled boundary metric has curvature tends to 0 rapidly. Originally it's compact, so we scale it. So this HI bar on this boundary actually has limit goes to the flat metric on R3. That's we know. So this sequence of metric has its conformal infinity R3, flat R3. So the strategy then is trying to show, in this case, the G plus metric, GI plus. So your scale is a GI, say it's rho I squared, GI plus. And then if you scale it, you scale the conformal factor, but this background Poincare-Einstein metric is the same. Okay. Should I write larger? Okay. Sorry. So I'm trying to say that this background metric stays the same. And this rho I plus square would converge. And the reason is because we have distance estimate. We already know this rho G bar, rho bar is less than equal to 1. Okay. So on a compact car, with rho I begin to converge essentially. Okay. And now the strategy is trying to show, in this case, this GI plus must go into the Poincare-Einstein metric, hyperbolic metric on the upper half space. So the key step is trying to show that this Poincare metric, so key step is showing that this GI plus actually turns to G with on the upper half space. Yeah. It's actually covered. There's this X infinity, but you take its universal cover. So key step is that. And if that happens, also, you want to show this GI infinity. This scale metric is again Poincare-Einstein. So you have this tends to G infinity plus is equal to rho infinity square, and this guy tends to G hyperbolic metric. And then you use the Liouville theorem I talked about to say that in fact this is a flat metric. That's the Liouville theorem we talked about the other day. Okay, saying that once you have Poincare metric, and then since you think it's a class of this adapted metric, also the conformal factor all satisfy PDE, you can use that PDE to say the metric, the limiting metric is a flat metric. And once it's flat, it contradicts with the property that this curvature has scalar as curvature equal to 1 at that point. So the limiting metric must be have curvature equal to 1 at the point, and that's the contradiction. Okay, so that we need some gain of regularity together. So the key thing is to show that, and then PDE argument to show this. Okay. So in the case of perturbation theorem, this can be reached because in this case, you have, we have assumption of perturbation theorem. We assume this Yamabe constant is a perturbation of constant in the neighborhood of the standard matrix. So passing to a sequence that Yamabe constant will tend to y of S3 by this inequality. Because this constant tends to 1, the limiting thing is hyperbolic metric. So we know that the limiting metric is hyperbolic metric. Or if we assume while L2 known tends to 0, then the only concrete Einstein metric is while equal to 0 is hyperbolic. So in either the assumption, we conclude the limiting metric must be the hyperbolic metric, and that's the only possible limit of everything. So we reach the compactness that way. So, so that's this theorem. And now let me show that suppose you do not have the perturbation result, how do you achieve the same program? Okay. So we talk about the proof of the main theorem, and then the only thing we now know is the Yamabe constant is bounded away from 0. So we know this guy is greater than delta, greater than 0. That's our assumption. And then we want to say this same program works. Okay, the limiting metric is on a standard model case. So in that case, what we do is the following. So here is a description of the step 3 for the main theorem. So this GI bar converges in the Gromov-Hausdorff limit to some metric, and rho I bar converges. Okay, that's the same. And the limiting metric is again Einstein. In the limiting case, it's Poincare. It's a conformal to an Einstein metric, G infinity. And now the key thing is the following. The key thing is, if we know this metric GI has scalar curvature in L2, if GI has scalar curvature in L2, that translates to decaying conclusion, decaying property of rescale metric. Because so this has something to do with it. We are in 4 dimensions. So L2 is an invariant property under rescaling. So your total curvature of Ricci square is finite. But you are now in this non-compact case. So that means outside this a large ball, the curvature L2 known is small as you want. Okay, and then you use the Bach equation to derive the Ricci L2 known. So this is Ricci L2 known. So you are in this setting outside a large ball. You know the Ricci L2 known is small, outside of real incomplete. And then what you do is you use this epsilon regularity to deal directly for ball centered outside Bn, and whose total curvature is L2 known small. And then you can see that translates directly to the Ricci decay of the rescale metric. Okay. So Ricci has, depending on the regularity, it has this little old decay. So the final theorem we have proved is really the following rigidity theorem. Sorry for the back and forth of this blackboard and so on. Okay, so the rigidity theorem is the following. So suppose we have certain space whose conformal infinities are 3, and it's asymptotic hyperbolic. And suppose we have a complete metric there, which is my limiting metric G infinity, and which is conformal to this metric, which is G infinity plus, we know is Einstein. And then we also know it has positive injectivity radius. There's technical detail. And the injectivity radius now have both interior and boundary injectivity radius lower bound. And the conformal infinity is R3, and we have this conformal, the scalar curvature of the metric is 0, and the distance function is bounded by 1. Gradient, the conformal factor has this control. And we also have Ricci decay. Then I claim this metric G infinity plus is the hyperbolic metric, okay, the standard hyperbolic metric. And the metric, the compactified metric, is the flat metric. Okay, so that's the honor theorem which one has proved. Okay, so now let me say a few words about how this is achieved. Okay. The proof is motivated by the strategy in the proof of Si Yuguang and Tian, and Dutta, Jebahari, and Li QS. Okay. So, as I say, what we do is now we are trying, okay, so this LQS inequality is to derive a lower bound. Say this volume is below bounded by the Yamabe constant. Our strategy now is we try to derive an upper bound of this. We try to say the right-hand side actually tends to 1 under the assumption I have. Okay? So instead of trying to give lower bound, I try to get upper bound. But we use the same strategy, same setup like before. So let's look at what we are trying to show. We are trying to say, to show this guy tends to 1 as t tends to infinity. That's what we are trying to say, because we want to show something hyperbolic. But let's reason this in terms of the conformal metric. So the thing we try to show is the ratio of the volume tends to 1. But we use 2 metrics. One is this t is the distance function in this hyperbolic metric, and we look at the gt theta, and then we also look at this, So in order to compute gamma t, we use gt theta to compute it, and that amounts to a conformal factor. So this is the conformal factor, which comes out is et over 2 to the d minus 1. And then corresponding thing for the hyperbolic metric is also the same way, but there is a sinh. But sinh and this exponential as t tends to 1 is the same. Sinh is et plus e minus t over 2, while t go to infinity. So to show the thing what we want in terms of this after change of this conformal factor, amount to show that along these slides, the area tends to volume of S3. This is volume of S3. So we are trying, so it's the same picture before. We are trying to show along this boundary of gamma t, this thing tends to volume of S3. That's what we did. But then we set up as before, and we try to compute this, use the same strategy as before. To compute the area of this guy, we use the conformal metric to compute the area of that guy. Okay, to use the same transformation. So we set it up. And now we have this conformal factor psi, which tells the difference between R and T. So we try to see what can we say about using this compute that area by this area. And they are related by this PDE, and the scalar curvature in this case at 0. We choose our compatibility, such is 0. So we are computing this stuff. And then the next observation is the following. Let's skip this page and I'll come back. The next observation is we have the Sokolov embedding of H1 into L6 in 3 dimensions. And that Sokolov embedding theorem says if psi behaves nicely, the energy gradient psi square, the H1 known, divided by psi to the 6th power has a lower bound. And that's the best Sokolov constant of the Sokolov embedding. And that is equal to this number. We know that. Okay. And so our strategy is to show that this right-hand side also have the limit the same as the left-hand side. So that means this side is actually the extremum function of the Sokolov embedding. And if you achieve that, you will see in the inductive step, how did you establish this inequality? You get an estimate of this volume of BT as we design. Okay, so let me fill in a little bit more detail about this step now. Okay, so let me go back 1 page. So keep in mind, this thing has a lower bound, and we try to get an upper bound. Okay, so we are trying, so there is this PDE, and we integrate psi on both sides, and we integrate. And when we integrate it by psi of gradient psi has the boundary term. So our goal is to compute this energy. So we try to get a suitable decay of the boundary as psi, gradient psi. And it turns out that's the stage where we need a Ricci lower bound, a Ricci decay. Okay. So the first step is to show that this U is the distance between distance function R and the T. And that's bounded function, but you show its gradient is also bounded. And when you compute its gradient, you also compute its second derivative, and that's to control it, psi, d normal. Okay, so anyway, I skip details here. And the detail says if the curvature is in L2 and it has a decay, then it's psi, d normal. You can ignore that. Okay. So if you have this big cutoff and you compute on this part, and as A tends to infinity, this goes to 0. And now we look at the energy term, gradient psi term. Okay. This energy works on this gamma R, this slice, a hypersurface, and we want to compute that. And this gradient psi square is R times psi 6 power, integration of psi 6 power. So you begin to see that it's bounded by scalar curvature times this volume. Psi 6 power is the volume. And you say that's little 1. And psi, there's a quotient. So you compute the upper S, the denominator and the numerator. And then the psi 6 power is just the volume. So we look at this. And the next thing is trying to relate that to the term we want. And that's the following. So the previous term boiled down the gradient size square to the scalar curvature estimate. And then you estimate the scalar curvature. The scalar curvature, GR, this is asymptotic behavior of this geodesic defining function. So you can have quite precise bound. Okay. So it's less than this. So this first line is quite straightforward. And the second line says, once you compute this on sigma r is less than equal to the GT gamma t. Okay, that requires a little bit of argument, but basically follow this type of step. So this is less than equal to that, and that's the volume of sphere. And after that, we are done. We are trying to say that this quotient.
You have like 3 more minutes?
Yes.
Like you have 3 minutes. Yes.
I have 3 minutes. Okay, I'm sorry. Then I'm going to finish soon. Okay, so I'm almost there. Okay, I didn't know my time. Yeah. So okay. So anyway, combining step 1 to 4, we get an equality of this quotient and say psi is the extremum function and equality everywhere. And that equality from this step shows that the volume of GT gamma t is the volume of S3. And that finishes the proof. Okay, so that finishes the proof. And then this. Okay, let me just put one remark and I finish the proof. In this proof, we use heavily the Weyl L2 norm is bound. Okay, but on the other hand, this L2 norm of Weyl is bounded is only used in prevent boundary blow up. It turns out the interior blow up part, the Weyl L2 norm is already bounded by the result of Chigger and neighbor. Okay, so you don't need that to prevent interior blow up. So that makes one wonder, does the L2 norm of Weyl condition is that, can we remove that condition? Okay, but that's going to be a deep theorem and we are working on it and we have some partial progress. And then the other thing is the sum of this result works on high dimension. And it turns out on high dimension, the difficulty is less on boundary blow up, but on interior blow up. What is the suitable condition to prevent interior blow up is the problem on high dimension, different nature of problem. So thank you very much.
Back to the statement of the rigidity of the upper half space that I just want to understand the slide that gives the rigidity for the upper half space.
Yes.
The character, can you go back to that slide?
Go back one slide.
Yeah.
Go back.
One that showed that.
Yeah.
No, the statement.
Yeah. That's the theorem I talk about.
Yeah, but you don't have the statement yet. You have
the last two sentences.
No. The statement, the actual statement of the result of the rigidity.
Yeah.
Yeah. Right. Okay. So what I'm trying to. So how do you get the reach decay? I thought is that for the that's the compact time metric? It's like is that a Moser iteration argument?
No, it's a direct estimate. Yeah. If you count the epsilon regularity as Moser's estimate, you have that.
Okay.
Yeah.
But
you want to say that since it satisfies Bach equation, the Ricci L2 norm on a ball is all the gradient of the Ricci is bounded by a suitable scale of the L2 norm and so on.
Okay. But that's like a half ball going
Yeah,
very large manifold. But you're not looking at like in the half space. You're,
No,
you're
I'm looking at the
upper half
ball
space.
here. Outside of it.
Okay, all right, so it's not just restricting, okay,
That's right, that's my conformal view.
okay. And you actually have delta, I mean, a concrete
Oh,
delta, right?
It should be 2,
Yeah.
but if I assume more regularity of my metric, I can make delta. There's a control of delta.
Okay,
All I need is some delta.
some level of decay.
Yes, yes, yeah. The rough estimate is L2 decay.
So in higher
Yeah.
dimensional case, in higher dimensional case, what is the decaying rate of this?
Yeah, it turns out this result, I stated for 3 plus 4, this part works for all dimensions, and it turns out in this case, the RISI in, I do not need to assume while in LD over 2 to get RISI in LD over 2. That follows. So I also have this decay. So this part of theorem is true for all dimensions. Yeah. But I have interior blowout problem. Yes.
Make a comment when you were doing like the upper bound,
Yes.
upper bound, sorry. So there you need really the dimension 4, right? To get the lower bound.
I didn't need this. I tried to show this is what under my solution.
So for that you have all the dimension, but this is the other.
Yeah, I'm trying. Yeah. The other side is the Sokolov embedding. I use Sokolov embedding. I say there's a best constant of H1 into L6, and there's a constant. And then my upper bound gives me the same constant. So my conformal factor is the extreme thing that forces everything to be identical. And that's
So that's what for all the dimensions. For all the dimensions.
I need to check yeah. Basically, that part of the difficulty is small. Yeah, we write it down for 3 plus 1, but we believe it works for all dimensions.
Okay.
Yes, yes.
Thank you. And do you think it's possible to do something like that, but not starting with a linear metric? When you have different, same result, but different metric.
Okay. There's a result, I should mention it, by Fan Wang, who showed that among these adapted metrics, if one of them is a compact family, the other is also. So once you choose, say, like flat S equal to n over 2 plus 1 half, that is a compact family under my assumption. The other family you use as a bridge. You can show the other family is also compact. So this result does not depend on the particular adapted metric chosen. But on the other hand, only this one tells me how to prove it. So in the same conformal class, sometimes you have one representative easier to tell you properties. That's what this is happening. It took us a long time to choose this one because we always feel we should choose a totally geodesic one. Yeah, we are forced to choose this one.
Thank you.
One question. When your boundary is not the sphere, but it's something else,
Okay.
you mentioned a uniqueness result, but how about existence?
This result does not depend on any ZC. So I have to think carefully because our topology, this H1, H2, we use the fact boundaries. And then the other place, many of these compactness results, we don't think.
Maybe finish here by This is a lot of work. Thank you so much.
Thank you.
And it's very nice.